I'm not sure if you see my screen now.
Yes, exactly. Just if you just full screen that, perfect. That's okay. Okay, perfect. Thank
Good.
you very much.
Okay, thank you, Dr. Ahmadi, and all other organizers, basically, in this unprecedented time, gathering and putting together this kind of workshop, which is really a good opportunity for me and others to learn from each other. And on a very important and trending subject, which is hydrogen production and hydrogen, basically, economy. And as 2020 and the pandemic was a turning point from carbon age to hydrogen age, referring to some of the pioneers in this field. And my talk today is about biomass-based hydrogen production. Basically, Dr. Ajar said all about hydrogen production, most like many things, but I just go and focus on biomass-based and more specifically supercritical water technology. Yeah, of course, I am a chair for ASME Ontario section, and ASME is the American Society of Mechanical Engineers. As the audience of this webinar, mostly, I assume, are mechanical engineers, was founded in 1880, strives to enable collaboration, knowledge sharing, and skill development across all engineering disciplines while promoting the vital role of the engineer in the society. And ASME, you are familiar with the codes and standards of it for boilers and many other applications. And ASME Ontario section was founded in 1917 with a headquarters in Toronto, Ontario, Canada, which I am now, and as a section under Northeast Region, District B of ASME. So just a very brief highlight of ASME Ontario section. Okay, 1917, it's the oldest basically section out of United States, and it's active since there. And the number of members, we have like more than 600 registered members and 12 executives, and almost we have around 10 activities per year, including workshops, webinars, tour visits, and etc. You see the map of here is the south of Ontario, Canada, near the border of United States. You see Niagara Falls, and you see in this map basically the university partners and ASME chapters of ASME Ontario. And you see Carleton, York University, Sheridan, Waterloo, McMaster, Ontario Tech Centennial College, and Ryerson University. Of course, there are other universities like University of Toronto and Windsor and Western Ontario, but these are just active chapters, and we are striving to enable and activate those other chapters. ASME is a community partner, working with companies that are familiar with you, of course, Boeing, Chevron, Microsoft, many companies providing engineering services like codes and standard workshops, certificates, and also many conferences in the field of mechanical engineering and journals. And maybe the most familiar for you is the Energy Resource Engineering Journal of ASME. And if you reside in Ontario and work or study in Ontario, you can join us and with these emails and links. If not, around the world, anywhere, we are open to collaboration, and you can contact, and we put on workshops, webinars, and activities, especially at this time, which is possible due to online situation. So yeah, so hydrogen production options and the role of biomass. Hydrogen production options, and the previous speaker talked about, and the sustainable options and different aspects of them. But in this one, we focus on biomass. So biomass is considered one of, as you see in the figure, one of the renewable sources of hydrogen. And we have also non-renewable sources of fossil fuel and hydrogen sulfide, H2S. And fossil fuels contribute to like almost 94.5% of current hydrogen production, but our aim is to produce hydrogen from renewables, which are biomass and water. So maybe most of you are familiar with water electrolysis, which is the most common way of water splitting and producing hydrogen and of course oxygen. And but biomass-based hydrogen is different in some ways and has pros and cons, of course, in comparison with water-based hydrogen. And there are some points here that biomass is considered a renewable material source for its production, and hydrogen is considered one among many products of biomass valorization. So basically, we have a biorefinery concept in a bigger scale, and when we convert biomass, it's not only hydrogen that's produced, but hydrogen is a valuable product and output. So I mean by this that in water you have this hydrogen basically as a valuable product, but here we have a variety of products, and you can take advantage of other products as well. So hydrogen is produced among others. And also, of course, biowaste is value added chemical waste is urban development. So most of the biomass is converted for this valorization and hydrogen production we focus on biowaste. So we, we take advantage of something that we want to get rid of it, which is a very common thing. So this is an incorporation of a waste to the value of the and this can be very important. Yeah. So yeah, just let me know if there is an interruption in my voice or anything. So let's move on and just say, okay, biomass is converted to many products, but why hydrogen? So besides what other speakers implied on the importance of hydrogen, we, with Dr. Dinser, my supervisor, published this, and this is a concept based on the initial concept of DOE, U.S. Department of Energy, which is called H2 at scale. And that shows us that how hydrogen plays a role as a baseline for energy sectors. So it can be integrated with gas-grade transportation, petrochemical, synthetic fuels, fertilizers, and many applications. And this is a baseline, and it is very flexible. So hydrogen is a flexible product playing a key role in the future energy portfolio. So whatever we want to go and focus on and advance in the technology, we need to map it in an energy portfolio toward sustainable energy development goals that we have. So hydrogen can play a very good role among other alternative fuels. So this is one of the reasons that we are very focused on hydrogen. And of course, here you see biomass as one of the renewable sources that can be converted first to electricity and then used for hydrogen production and or directly turning into hydrogen-rich gas and then purified in the form of hydrogen. So before going into the main, basically, technology and going into chemistry and stuff, let's just see where biomass-based hydrogen is placed among the rainbow and the variety of hydrogen production technologies that we have now. So this is from a review paper of 2020. Again, the same paper. You can find it in Energy Conversion Management Journal. So this is based on the very recent life cycle assessment of different different hydrogen production technologies. You see biomass gasification as a representative for biomass-based hydrogen here, and you see it's kind of not meeting the target, but it's close. And these are not decisive because for integration it can be changed. But anyways, biomass gasification is in the midway kind of. It's not that far from commercialization, like photobiological conversion or photoelectrochemical water splitting here, but it's not also yet commercialized. So it's promising to work on and practice through integration, through system development, etc. However, with all these technologies, it's very, I don't know, like interesting maybe to know, but it's sad that it's just less than 1% of hydrogen is initially produced from renewable sources. So yes, some can say like we have electrolysis of water splitting through electrolysis, which is not from steam reforming of methane, but we cannot consider that biomass or let's say sustainable hydrogen production on green hydrogen production. So that electricity, where does it come from? So if we do the analysis and if we refer to the report of Hydrogen Council in 2020, which this figure is for, we see that less than 1% is really from renewables. So we are so far, but it's really trending now. And in my opinion, 2020 was the year, and 2021 you see like many companies going toward hydrogen. Based on this, so you see the cost and global warming potential, which is the factor for environmental friendliness of hydrogen production technologies. And also cost is very important, of course, for commercialization. So you see that you see that the steam methane reforming has, for example, high global warming potential and low cost. And based on this concept, we just proposed this kind of transition to green hydrogen production in the same paper. So this is from methane reforming and coal gasification to photobiological, photofermentation, and photoelectrochemical. These processes are low temperature and very low exergy destruction, and also very environmentally friendly, as you see. Low global warming potential, less than 4, and from renewable sources. We have here methane reforming and coal gasification with low cost, less than $2 per kilogram. So $2 per kilogram is the kind of a measure, and it's a DOE target, U.S. Department of Energy target for commercialization of hydrogen. So if we go under $2 per kilogram, we are good, and we can think about commercialization. And of course, these are non-renewable sources and established industrial processes. So you see, from black hydrogen, we go to like green hydrogen with low global warming impact, but the cost is high, which means that we need more advancement, and it takes longer. So in long term, we have these technologies, and in mid-term, we have biomass gasification, we have wind electrolysis, and we have nuclear thermal chemical water splitting cycles. But this is not decisive. I mean, like, these technologies are all evolving and all integrating, and also at the same time, the energy portfolio is evolving. So probably in some cases in near future, this wind electrolysis become very commercial because the production of renewable electricity goes very up, and we can basically, with a lower cost, produce hydrogen. Okay, let's come to biomass. So now we kind of know with this that where biomass-based hydrogen is placed kind of in hydrogen economy portfolio. And then we just move on and to see what is biomass, like what to do with biomass, and etc. So biomass is evolved as well. So we were from like food and from like very basic biomasses and edible biomasses like sugar, starch, and which are interfering with food cycle, and they're not very attractive. Now we move to second generation of biomass, which is agricultural waste and municipal waste, and they are still slightly interfere with food chain. So because there may be alternative uses for example, wheat straw and other similar agricultural waste. And highly dependent on land and water. This is another problem. So we need land, we need water to grow this, and these also contribute to some carbon footprint at the end. So we moved in the last 2 decades, like from 2010, lots of research is going on algae and algal biomass. So algae promises a very good source for biorefinery overall and hydrogen production. Why? Algae doesn't interfere with food chain and very slightly dependent on land and water. You can grow algae even without land. You can grow it artificially, and you can grow it with a very, very low amount of water. So algae is very promising now, and we are finding, let's say, interesting aspects of algae day by day. And fourth generation of biomass, which is very at the early stage, it's about microorganisms and also genetically modified algae. And of course, there are also no interference with food chain and no dependence on land and water. So how to convert these biomasses? So we have second generation, third generation, fourth generation, let's say. How to convert? What are the possible pathways for hydrogen production? So we have, so again, this is just a brief introductory thing for just showing what are the options for going from biomass to hydrogen, but there may be other technologies, evolving technologies, but the main technologies and basically literature technologies are just summarized here. So we have thermochemical conversion and biochemical conversion. We can split in these two rules based on the initial energy, driven energy of the process. We have thermochemical conversion, which the heat is input, and biological conversion, which is photonic through the microorganisms and biological processes. So thermochemical conversion and biochemical conversion are debating, basically. We cannot say which one is very better, but pros and cons against and advantages and disadvantages. We can say that thermochemical conversion is faster, higher yield of hydrogen, and less sensitive to condition. For example, in fermentation, when you want to produce biogas in wastewater treatment plant, you need to just keep the temperature at almost 35 degrees of Celsius. And if that changes, like go 1, 2 down or up, the process is gone. So it's very sensitive to biological conversion, but it's not the case for thermochemical conversion, which is a good thing in most of the cases. And biochemical conversion or biological conversion are less energy intensive because they're in lower temperatures. That's a very promising point, and we don't need to develop the integration of high temperature like facilities and or providing a lot of heat and consuming a lot of energy. And we have more control on products because it's very gradual. We can just set the reactions and the process in a way that we extract different chemicals in each step. So it's not just once at once and producing syngas. So these are pros and cons. So biological conversions are also very interesting, but the focus of this talk and today's talk is supercritical water gasification, which is a very promising among thermochemical conversions for these reasons. So advantage of supercritical water gasification. So conventional gasification, if you are familiar with, are using heat in temperatures of 800 to 1,000 degree, let's say, maybe 700 or above, but for lower temperatures and 400 degrees Celsius, supercritical water gasification is a very good choice. So lower temperature, less energy consumption, and it's a very promising point. Higher hydrogen yield, favorable for integration in combined power and hydrogen cycles because we have a high pressure, high temperature gas output, and we can, let's say in a continuous manner, we can integrate with power generation and turbines, and able to convert wet biomass. This is also in process point of view is an important point, that we can convert easily wastewater and other wet biomasses without the limitation of moisture. So usually for other conventional technologies, when we have less than 30% moisture in the content in the biomass, we are able to do the process, not with more than that. But for supercritical water gasification, the interesting point is doesn't matter how much moist and how much wet is our biomass. And able to convert hazardous waste, which is very important recently in the world. We want to get rid of nuclear waste, plastic waste. Like NASA had a project in New Mexico State University, I remember, for just using this technology and pyrolysis, which was another technology of thermochemical conversion for converting the waste of NASA. And this is very interesting. And also catalyst durability and activity. This should not be here. And biomass characteristics. So, okay. So we mentioned the advantages of supercritical water gasification, but we want to go into the process and see what's going on and how we convert it in supercritical water gasification. So first, we just need to know really what is biomass and what's the structure of biomass and what we are going to do with it. So this is a walnut shell, the study that we did like 5 years ago in University of Tehran. And this is the structure of walnut shell just simulated. You see these greens are cellulose and hemicellulose and lignin. And hemicellulose and lignin are binding the cellulose in the structure of the biomass together and making it like secure from damages, basically, and putting together the cellulose, basically. And of course, biomass contains carbon, hydrogen, and oxygen mainly, and we have also nitrogen and sulfur with like a small amount, but usually we write it like this: CXHY and OZ. So this is a kind of a formula for biomass structure, and depending on the nature of biomass, that indexes can be done. And we have cellulose, hemicellulose, and lignin. The availability of cellulose, hemicellulose, lignin, and the ratio between them is very important. We know kind of, it's not very precise in the literature, but we know kind of that more availability of cellulose, which is an easier polymer to degrade, basically, is a key. So if we have more cellulose available without lignin and hemicellulose bounded, we are good to go for gasification. As you see, just briefly, cellulose contains glucose subunits in a linear polymer bonded with each other and can be break down, and we will talk about the reaction mechanisms. And hemicellulose also a similar stuff, but with some side chains of xylose and other 6-carbonate polymers. And lignin is a problem kind of, so in supercritical water gasification, because lignin is a nonlinear and not very specific shape, and it's just aromatic. It's a combination of aromatic compounds like phenolic, methoxyl, and these kind of aromatic compounds, which is tough kind of to break and to degrade into liquid and gaseous products. So this is about biomass. So more availability of cellulose is a key point. And what about the supercritical conditions? So what is supercritical water, and why supercritical water gasification had those advantages that we talked about? We go a bit into chemistry, but I'm sure I will not talk about a lot about chemistry because I know most of you are mechanical engineers. But anyways, we need to know about as energy engineer and when we deal with hydrogen production. So you see water. So water we have in 3 phases, like solid, liquid, gas, and based on temperature and pressure. You're familiar with this figure, but over the critical point, which is temperature of critical, which is 374 degrees Celsius, and critical pressure, which is 22.1 megapascal. Water turns into a supercritical region and supercritical. So you see here, this figure is also from one of my papers, in 25 megapascal, which is bigger than 22.1. When we go from temperatures from 300, let's say, here, to 500 around, so we go through the critical point, and we call this area a transcritical region. So this transcritical region is very interesting. Why? Because you see the properties of water changing very sharply from 300 degree to 500 degrees Celsius. So this sharp change of water properties probably changes the properties of water itself in solving materials and in applications. So this was something that was found just very suddenly by Model and colleagues in MIT, 1978, when they were playing with the normal gasification, steam gasification, and they just played with the temperature and pressure. And once they just reached the critical point, they noticed that they have a lot of gas production. So where does gas come from? Wow, all of a sudden. So they noticed that, wow, we're passing the critical point. So this transcritical region is very important because the properties of water change, and we will see how this change in properties promises higher dissolution of organic compounds and biomass into hydrogen and like low-grade hydrocarbons. So in supercritical condition, as you see, density coming down, ionic products coming down. So the ionic mechanism turns into free radical mechanism in transcritical region, and also dielectric constant coming down. The reason is that we have hydrogen bonds between water molecules. So you see, this is hydrogen bonds between water molecules. This is a water molecule. So when we turn into transcritical region, it's very harsh situation because it's sharply changed, and that electron clouds on the bonds change rapidly, and basically they found out that this hydrogen bond disappears and emerges and disappears. So in a very recent paper in Journal of German Chemical Society, they just observed that there is no hydrogen bond in supercritical water. But again, there was another claim after that, that no, it disappears and emerges. So this property of hydrogen bonds makes water a non-polar solvent. So water is a polar solvent and a polar structure. But the linkage and the weakening of these hydrogen bonds causes water to solve basically inorganic compounds, like like biomass, and turn into non-polar solvent, and gives it a very unique properties and favors free radical mechanism, which is can damage the biomass structure and degrade the biomass. And also this appearance and emergence of hydrogen bonds gives the dual characteristics to water. So the dual in water in supercritical condition, we cannot say it's fluid, liquid, or gas. It's something between. So that comes from this. So this is very interesting about supercritical conditions. So from that 1978 that I told you, processes have began, and in the 21st century, many papers came out and many research institutes developed this technology. So hydrothermal gasification for hydrogen production. Furia, if you just may let me know how much time I have.
Can you hear me?
Yeah.
You have 6 minutes left. If you just...
Oh, wow. Give me like 5 minutes more.
Okay, sure. Keep going. Thank you.
So, thanks. So we see the reaction mechanism. So just briefly, the degradation under these conditions and into 5-hydroxymethyl furfural, which is a very important intermediate in this process. And here, the very important step is when we reach from biomass to these alcohols, aromatics, and aldehydes and phenols, we need a proper catalyst. So in fuel cells, you know, the catalyst is a very problem as a key point. And also in this supercritical water gasification, catalyst is very important, also in many biomass processing technologies. So proper catalyst is a very key point in this process. So this is also a reaction pathway from a paper of researchers from University of Saskatchewan. And yeah, and we have these reactions, main reactions, and we need to catalyze in favor of hydrogen production. So what are the catalysts that we use usually? So we have alkali catalysts like potassium hydroxide and etc. And we have transition metal catalysts, which are very promising. Many research are done on nickel. Ruthenium is very important and very promising for hydrogen production, and they're very good in improving the reforming process and cracking. But the main problem also is cost with, for example, ruthenium. So an emergence of new catalysts is about carbon-based catalysts, like activate carbon and char, which are derived from biomass themselves and very promising with very low cost and carbon footprint. So what we did, just briefly, in our experiments, this is our lab in University of Tehran and our setup with my colleague, Dr. Salimi there. And like 5 years ago, so we did some experiments on algae and agricultural waste. So we found out an interesting point once, that if we characterize the hydrochar, the solid product, which is a problem in supercritical water gasification because of agglomeration, because of plugging in the reactor, and etc. So if we turn back that hydrochar into the process as a catalyst, the hydrochar was so porous and rich in alkali metals, which has catalytic effect. So we turned back just as that catalyst, and we saw a promotion in hydrogen production, which was a very interesting point and published in Bioresource Technology. And you see the structure of that hydrochar after supercritical water gasification, and you see the regular pore matrices here that gives it a high surface area, and also at the same time it was rich in alkali and alkaline earth metals. So these metals are very promising for promotion of water gas shift reaction here, which turns carbon monoxide, which is something that we want to get rid of it, into hydrogen. So this water gas shift reaction promotion is very important. So, and this is also wheat straw hydrochar. This is for algae, and this is for wheat straw. And you see the pore channels and the high surface area. Yeah, and we saw and we compared these two char, and we understood that AAMs, or alkaline and alkaline earth metals of algal hydrochar, favored hydrogen production more than even surface area. And this was other work performed with my colleague Dr. Nourouzi in University of Tehran. We impregnated the gamma aluminum catalyst with nickel, and we saw a promotion in hydrogen-rich gas production. And also we made an alloy of nickel with iron to more tar cracking in the process, published in Energy Conversion and Management. And in the last 5 years, there have been many research on hydrochar, which are promising byproducts of the process. This one is by Dr. Nanda, Sonny Nanda. I'm not sure if he's in this talk, but they have been doing a very great job in University of Saskatchewan in Canada, and they're like pioneers in supercritical water gasification. Encourage all to just go and study their works as well if they're interested. So you see many fruit waste, basically, orange coconut shell, banana, aloe vera, and others. And you see the porous structure and basically porous surface. But in terms of demonstration of hydrogen, so this was some advances in this technology. Demonstration of hydrothermal gasification for hydrogen production. So, okay, we know all this. This is very good, but what we are in terms of industrialization, the real plant, something. So this is a plant is being developing in China, and Xi'an University, I guess. And the construction of the solar concentrator accounts for most of the environmental emission during the construction of the system. So they did an environmental analysis with life cycle assessment, etc., and they found out that this solar reactor and this construction of this solar reactor and also concentration of solar energy is very has a higher carbon footprint, and this is a key to solve. This is a basically problem to solve in this technology. But it's a very good news that they are developing. Some folks in Netherlands, in Delft University of Technology, also developing pilot plants of supercritical water gasification, and also Australian National University with Cyril. They're just publishing, the papers are coming out on integration, very promising integration of supercritical water gasification with Fischer-Tropsch synthesis, which makes long-chain hydrocarbons and green, basically, diesel for applications. It's all solar-based because they have very good solar energy there in Australia, and it's a very promising point. So the key is it's very good to make an integration, because supercritical water gasification, with all its advantages, has a problem of how we make that energy to giving that much pressure and basically temperature to water. And the answer is, if we can couple with solar energy or nuclear maybe, or like those high temperature, mid-range temperature technology heat sources. So this is a very key point in this technology. So I'm gonna conclude and wrapping up. So challenges of supercritical water gasification after all is char agglomeration and plugging, corrosion as a result of high pressure and temperature, and also it's good to continuous reactor development, and safety concerns, very high temperature, pressure, 22 megapascal, 1 megapascal. So material development is very important on this, and catalyst durability and activity is a key point. It's very important, and proper integration, very important, with solar nuclear heat as energy input and proper downstream processes such as Fischer-Tropsch synthesis. Just as this is biomass-based hydrogen production, I want to just briefly show some of other technologies besides supercritical water gasification, biological technologies. Very promising one by International Energy Agency. This is very low carbon footprint, just photosynthesis of algae and algae production here, and turning into the photobioreactor in presence of catalyst and sunlight, turning into hydrogen. Very promising, but needs development, and not yet for large scale hydrogen production, just for small scale yet. And some other integration you see with biogas plants, so we can basically separate the CH4, methane, and biogas, and reform that methane with solar-based reforming to have a very green hydrogen at the end, because our source is let's say wastewater, and our energy source is sun, which is very interesting. And also, overall, in biomass-based hydrogen production and biorefinery concept, these integrations are very important. So it's not the technology by itself. They are growing together, basically. And this is one of other example of gasification in supercritical water media of digestates, which comes from anaerobic digestion plant. So turn that digestate in value-added product. We know we have the biogas, okay, that's fine, but we have some digestate, and we turn it into also products and gaseous products and else. Overall, the concluding remarks. So hydrogen economy is a progressive multi-decadal project with gradually in transition to marketplace, and it's expected to be fully commercialized within a decade. So this is like, we need to be fortunate for this, but I think this is a rational that we, in 1 decade, maybe now we can say that we have hydrogen because it's evolving very fast and faster and faster. And because of the very promising points about hydrogen that I just mentioned. Biomass is a renewable source of hydrogen, which is in some cases, 3rd and 4th generation, doesn't interfere with food and water supply. This is very important in the case of algae, for example. Biomass-based hydrogen, along with other biomass conversion technologies, promises a sustainable biorefinery concept with the aim of waste management and circular economy. So in a bigger concept of sustainable development goals, circular economy, waste management, like sustainable energy, we have these technologies working together to reach those points. And also hydrothermal gasification is a developing technology for thermochemical conversion and of biowaste into hydrogen-rich gas. So the key question, is it possible to have these technologies commercialized with respect to DOE targets? The answer is improvement in these technologies is not enough. I wish we could have it in the panel, but I brought up here so we can talk more in the panel. Works with other chains of hydrogen economy, such as hydrogen storage, fuel cell development, and etc. So it's not just hydrogen production. It's a chain of other parts of hydrogen economy working together to make it commercialized and reaching this value. Proper integration, considering the limitation and local advantages, is a key to make advancement technologies. Local advantages are important, so technology set based on the local conditions and also the limitations. Other energy sectors as well as electricity grid need to be considered beside the well-to-pump hydrogen for energy sustainability. So we have well-to-pump hydrogen from source to hydrogen, but these are in the whole energy map. And in energy portfolio, we need to put them in a sustainable manner. So this is important as well. Which biomass to hydrogen route is best for hydrogen production? Nobody knows, all and none. So all of the hydrogen production technologies and which biomass to hydrogen technologies are a part of them are evolving together, integrating together, and they are good for certain conditions. We cannot say which one is the best. And question, comments, and sorry if I exceeded my time. Thank you.
Okay, so thank you very much, Dr. Safari. And if you can just share the screen. So. Okay. Okay. So thank you very, very much. And there are a couple of questions. I just gather all of them.